just because that there's the possibility that we might, re-Columbus something, that, just because it's a possibility doesn't mean we shouldn't do it. It just means we need to think about it.
Welcome to the AZ Tech Podcast. I'm your host, Hamid Chojai, a tech enthusiast and entrepreneur. Recently, my wife and I sold our software companies and we're investing $10 million in Arizona's tech ecosystem. As a way to know what's happening in Arizona, every week I get to sit down with some exceptionally talented people who are doing some cool shit. All right, let's go. I'm here with Dr. Daniel Jacobs, a researcher at ASU's School of Earth and Space Exploration. Hey, Danny.
Hi, how's it going?
Good. How are you?
I'm good. All right.
Awesome. All right, let's jump right into it. You're doing some really cool research about the origins of the universe, and why don't we start there? And there's a bunch of other things I want to talk to you about based on your background in physics and astrophysics and the type of research that you're doing and satellites, and it's going to be a fun topic.
Well, there's a lot to talk about, and,
Yeah.
and I like to talk. So the cosmology stuff is, humans have been learning a lot about our universe, on the biggest scales in the past 40 years or so, 50 years, to the point where we know, we have this origin story in the Big Bang, and we know sort of rough time history period, 14 billion years or so went by, and then here we are.
Right.
We know that. But there are a lot of huge holes, actually, that are kind of conundrums. In fact, so you might know some of them, like the fact that we think that most of the energy in the universe is in what we call dark energy, which basically just means we don't know what it is. And then the rest of it is mostly in dark matter, which, again, we don't know what it is. And the main difference being how they interact with matter, how they do, with the kind of things that they do to the universe. But another big mystery that we still don't understand very well, and so that's sort of mysteries that have been exposed by measurements.
Okay.
We've done a lot of measurements with satellites and ground-based observatories and everything from looking at galaxies and how they move. We can see there's invisible stuff there. That's what dark matter is. We can see galaxies flying away from each other faster than we'd expect, and that's what dark energy does. But there are other mysteries too, like, for example, why are we here?
Right.
The universe started off as this lumpy gas of hydrogen, basically, and collapsed under gravity, and eventually formed stars and galaxies and stuff, and us. But if you try to make stars with just hydrogen, they don't. You can't make them. In fact, this was a big problem about 100 years ago or so. And it was solved by adding metals, which to an astronomer just means anything that's not hydrogen or helium, like carbon is a metal.
Okay.
Oxygen is a metal. If you salt a little bit of that stuff into some hydrogen, you can make a star, and it basically acts like a catalyst. But the universe, when it was born, didn't have metal.
It was just hydrogen.
Yeah, a little bit of helium.
So how, like, okay.
So that's a big mystery. How did stars even form?
All right.
And no one knows, really. And it happened we know it happened not that long after the Big Bang. We know it happened pretty quick, actually. The universe wants to make us. The Earth is 4.6 billion years old. That's a good fraction of the age of the universe.
Right.
People tend to think the universe is, mind-bogglingly huge and old. And 14 billion years is a long time, 13.8, whatever. But that's not that much longer than 4.6 or whatever billion years the Earth is.
Right.
The Earth has been around most of the age of the universe.
About a third of it.
Yeah.
Right. So how do we know, like, that hydrogen by itself can't form, like just the gravitational pull doesn't form the necessary components of like stars?
The basic quantum mechanics of how stars fuse. Stars are powered by fusion.
Okay.
You put enough molecules together, enough atoms together, they start to stick together, and when they do, they release energy. That's what fusion is.
Right.
So there's hydrogen in a star, and it gets pushed together, it fuses, and a whole bunch of energy comes out.
Right.
Think of it like there's this deep hole. That's where two atoms are sort of smooshed together. So there's a little bump that you're going to push them up and over, and then they're going to go falling way down. When they hit the bottom, that's sort of like
the explosion,
pushing them together. The thing is that the bump they have to push two hydrogen atoms together is really big. You got to really smoosh them together, and it's just not. It doesn't work out if you do the math. Like you can't
like the gravitational pull of even if you have plenty of hydrogen is not enough to create the initial.
You would
sparks.
get a much bigger star. It would have to be a lot bigger than ours is. For example, if our star was just hydrogen, it would be enormous.
Right.
To get it to burn.
So the question is like, why couldn't it have started out with really big ones?
It did. And that's what we think happened. But they're really weird. There's no modern examples of them.
Okay.
They call them population 3 stars because astronomers give things names. So there's theory. Of course there's theories.
Okay.
Of course there's theories. People think they know.
Right.
But they don't know.
Gotcha.
So what I want to do is find out.
By setting up experiments.
Yeah.
And that's what your research is about.
That's what it's about, yeah.
Okay.
And it turns out if you can observe we've come up with this observable, and that is actually looking at the hydrogen itself in the early times. It radiates radio waves. The hydrogen atom is the smallest atom that there is.
Right.
One proton, one electron. Can't get any smaller than that. It radiates a radio wave because of radio emission. Like so, for example, if you look at the sun through a grating or through a prism or something, you see all these lines, right? These are atomic lines that radiate. There are lines all the way from radio up to, above visible, like where our eyes can see. They're all over the place. But they're generally pretty small. Like they're photons, right? They're really narrow wavelengths. They're nanometers we talk about.
Right.
They're small. The hydrogen atom radiates a radio wave 21 centimeters in wavelength.
Okay.
That's literally, macro size. It's this big.
Right. A little more than a foot.
Yeah, about a foot. So that enormous wavelength.
Or actually less than a foot, I guess.
Yeah, a little less than a foot, whatever.
Yeah.
I'm a cosmologist, I think, in orders of magnitude. It's a foot, it's a mile, it's between there.
Gotcha.
It boggles my mind to think about the tiniest atom and this enormous wave comes wiggling out somehow, right? It's
of the tiniest little thing, right?
Yeah.
I see what you're saying.
It's weird.
So
it's weird.
So you can detect these wavelengths, and like you're trying to detect the ones that were generated at the Big Bang,
way back in the day. Yeah.
Okay.
So people look at this stuff in modern times, other galaxies, our galaxy, and in fact, it's one of the main observables that's been used to show that dark matter exists. Because the radio it's like a GPS.
Right.
It lets you track the matter really precisely, and so you can see it's moving like that. There's some hidden stuff there. Anyway, so we can see it in local galaxies. There's a little bit of hydrogen down in every galaxy. You can track it. But the stuff that's at the very dawn of time, it's far away. It takes time to get to us, right? The look back time, the light cone is such that if you tune. So you go to the very early universe.
Right.
You have a hydrogen atom, a 21 centimeter line photon comes out, and then the universe does its thing, which is to expand.
Right.
Because it's sort of just coasting after the Big Bang, basically.
Right. After the explosion, everything is moving apart from one another.
But it's because space is expanding.
Okay.
Not because everything is moving.
Oh.
It looks like it is, but it's just space that's expanding.
Okay.
Take raisins in a raisin bread.
Right.
The raisins aren't moving in the bread, but when the bread bakes, they get further apart. Or you take a balloon and you put some dots on it and blow it up. They're not moving. The dots are still the same spots that you drew them, but they're getting further apart.
Okay.
This is the same idea. And the balloon is a really good example because draw a wavelength on it. Draw like a sign, like a line.
Right.
Blow it up, the line gets longer and longer.
Right.
So too does the 21 centimeter wavelength gets longer.
Okay.
And this is true for all radiation in the universe. As the universe expands, it gets longer. So it's coming to us for 12 billion years, it's been traveling to us, and the universe has been growing and growing and growing. So by the time it gets to us, it's grown from 21 centimeters to 4 meters, depending on how far back you're looking.
Okay. So when you detect these, like, what's the hope? Like, what are you hoping to be able to determine?
Well, I mean, if you think about what you might see, what might you see? You might see hydrogen, make a map.
Okay.
And you can, at different wavelengths you're tuning to, you're looking at different times.
Times.
Yeah.
Okay.
So you could make a 3D cube, like a 3D map of where things are.
Where things war. Like 12 billion years ago.
Yeah.
And your hope is to detect the other metals, or to detect
so there's matter and energy out there doing whatever they're going to do.
Right.
And so one thing people think is that when stars start to exist, we know they do because here we are, they're going to ionize that hydrogen. They're going to burn it away. Hydrogen is a tiny little atom. It doesn't take much to ionize it.
Okay.
In fact, if you look around our universe, like locally, there is no hydrogen between galaxies. It's all been burned away. It basically gets sunburn.
Okay.
Literally.
Suns
burn.
Suns burn.
UV light burns it, and by burning I mean just turns it to plasma. It's just gone. So we think if we look at some distance, we'll see hydrogen, and then later it'll just kind of disappear. And in between, you'll see these holes, like Swiss cheese holes.
Yep.
Where stars start to burn holes away. And there's other stuff too. Like before that even happens, you can see like it get hotter. You can actually measure a temperature of this signal. It's not just there or not there. It's like more or less, and so you can actually measure a huge volume of the universe and start to do some, you can do some really powerful statistical stuff.
And where are you guys in this research?
Well, it was a new idea, I don't know, about 20 years ago. And there was about a decade of theorists sort of sorting that out and figuring out what might we see, the questions you're asking. These are really like hard questions to just predict.
Right.
What, given a guess of what might have happened, what would an instrument like see? What's a good kind of instrument? What's a bad instrument? And so about a decade ago, we were building the very, very first instruments. We're talking about wavelengths that nobody really uses. The universe decides where we get to look, what frequencies we get to look. And it turns out about 2 meters wavelength, which is a look back time right around we think this transition happened. That's FM radio. So 100 megahertz, 101.9.
So we do use it.
Oh yeah, we use it all the time, just not for listening quietly to the universe. We use it for.
So does that create a challenge trying to listen to the?
Yeah.
Okay.
It does, in fact, create a challenge, and so that means we need to build these things far away from humans.
In space.
Well, we started by going to Australia.
Okay. Because they don't have FM over there.
They in the deep in the outback, they have 1 person per square Delaware.
Oh, I got you.
It's just not a lot of people.
Just in unpopulated areas.
Not a lot of customers for mattress advertisements and whatever else.
FM radio has.
Yeah, and so there are places on the earth where it's quiet.
See, podcasting is good for that, right?
That's right.
That's right. We're not on the airwaves.
Except for sometimes when they are, like when I'm driving in my car and here's a podcast on the air. Anyway, yeah, there's a few places.
Okay, so continuing like where the research is at. So you guys eventually came up with the instrumentation.
Yeah, so we built a couple of different. When I say we, I mean humans.
Okay.
Generally, there's a bunch of different groups around the world trying to do this, and everyone has their own, unique
approach
spin on it. Yeah, and there's about 4 or 5 or 6, depending on how you count, experiments, and they're all different and weird looking. And we're talking about, kind of a lot of collecting area, a lot of metal on the ground too. It's not a small thing,
right?
Because your wavelengths are big.
Okay.
You need a big dish. You need a big receiver of some sort. So we're now building the second round of these things. The one that a lot of us are working on right now is called the Hydrogen Epoch of Reionization Array. It's It's got 350 dishes. Each of them are about 40 feet across, and they're all packed together in a single clump.
So they can act as a single dish, essentially.
Essentially, yeah. And that thing's actually in South Africa, not Australia.
Interesting.
And there's quite a renaissance in both South Africa and Australia in radio astronomy.
So they collect the data, send it to researchers around the world.
It's more like it's a collaborative work. So we go there all the time.
Okay.
And help put it together. The local help, they manage the project locally. They build most of it, and then people from all over the world are building the bits, like the receiver bits, the electronics, and that sort of stuff, and go and plug it all in.
What's the big question that you're hoping that this research is going to answer? Like, what are you after personally?
I think it's fun. I don't know.
But what's the question like the answer to what question is your pursuit? Like, I know it's fun to be researching these things, but like, what is the motivation factor? Like, where are we coming from, or where did we come from?
Where did we come from, and why are we here, and not not nothing?
Right.
And why is it that we get the kinds of galaxies we do? They're not what you might expect if you were to just sit down and try to imagine what would form from a bunch of hydrogen gas collapsing. You would not probably predict what we've got. It's kind of hard. Nobody can do that because we all know what we've got.
Right.
But it just all doesn't quite gel. So that's why so many telescopes are spending so much effort in looking so far back. That's when it all happened. That sort of very brief window when stars formed for the first time, when galaxies formed for the first time. James Webb Space Telescope. This is one of the big questions. It's almost hard to phrase as a question, right? Like, why do we have what we have?
Yeah. So, I mean, there's sort of like the question of, like, why are we here, which might not be answerable, versus, how did things come to be the way that they are?
And
which seems to be more answerable.
Why is a bad question. It's how is a better question, because who knows why, but how is definitely an answerable question.
Yeah. Mm-hmm. So to answer the how, the big sort of hole that's missing in the origin story of the universe is, how did other molecules form, or other
metals,
not molecules.
What is it? Yeah. How did
elements?
How did elements get here? But I honestly am most interested in the cosmology questions, like, what is dark energy?
Right.
Is it really an energy? Like, what is dark matter? These just touch everything, and they're just big question marks, and they've been question marks since I was in college, and drove me crazy then. And it's such a big question that you have to bite off a little thing and try to answer smaller questions of just, smaller questions like, how did all the stars and galaxies form?
just a tiny little question.
Yeah. There's so many different options, for example, for dark matter. There's so many different options of what it could be.
Right.
Everything, almost none of them have been suitably eliminated, in my view. And each one of them requires a different kind of way of tackling a detection, or some kind of direct detection. People are looking. You can write down, I think maybe it's this kind of particle, and then you can devise an experiment to look for it. But if you write down a different particle that could equally solve the problem, you would have a completely different experiment, or maybe not even one that would work on Earth. It may have to be done, astrophysically somehow, by making a prediction about what you might see up there, and
by like sending satellites to do the observations,
or just astronomical observations.
Oh, okay, like of other stars and things.
Yeah. So for example, people have shown that there's a little bit of evidence that maybe there's an excess of energy in the local galaxy,
Yeah.
That could be evidence for annihilating dark matter, maybe, of a specific flavor. It's, there's more than 31 flavors of dark matter.
The Baskin-Robbins of dark matter.
Yeah.
So as part of this research, you've also dabbled a little bit with CubeSats. Or what are they?
Small satellites.
Small satellites that are roughly the size of cereal boxes, apparently, right? Like so, how did your research lead there, and what can you tell us about that research?
Well, I mean, personally, it's been more of my checkered history of just doing things that are kind of attractively cool and interesting and a little bit out there. So in grad school, to pay the bills, I worked at a satellite lab that was in the physics department of the university I was at, and that's it's just kind of fun to help. I mean, mostly it was an educational thing. The origin of being able to make a very small satellite and get it to space means that students, people, or anybody can make a satellite.
Right.
And that really opens up a lot of possibilities. It's no longer NASA. It's just, or the military industrial complex putting things in space. You could do it.
Right.
On your kitchen table. It would be your obsession for about 2 or 3 years, but you could do it.
What's the cost of putting a small CubeSat into space?
You can get it to space for free.
Oh, really?
Yeah. There's a NASA program that you can apply to, and if your satellite isn't dangerous, usually they go to the space station, so and the astronauts kick it out the door for you.
But I imagine it's got to be extremely competitive to get into one of those. No?
No.
I see a side project coming up.
Yeah. You got a maker space? Go for it, man. No, anybody can do it. And that's, I think, what the cool thing. You asked about, how it's related to my research right now. And I think the answer is that the Earth is a noisy and, kind of annoying place to build precision instruments, like the kinds of things we're trying to do for cosmology. Space is quiet, stable. It's far from us. It's further away than Australia, which is about as far as you can get on the Earth. So we kind of see this as a long-term development project, getting good at putting instruments in space. And we're involved in projects to develop all the way up to small instruments to go, in near space just to test how they do, kind of thing, all the way up to trying to build a big array on the far side of the moon, which is it's been the dream of the the science fiction nerds for about 50, 60 years.
The big, ever since we landed on moon, but a big array of what?
Well, the current plans are mostly to try to build like a low frequency array, because on Earth you're under the ionosphere.
Okay.
The ionosphere
I got you. It's related to your research still, to be able to detect those 2-meter waves.
Yep. Or beyond. And so we're talking like 10, 20 meters.
Gotcha.
So there's a lot of other cool stuff you can do. You can observe at 20 meters, which is that's a long wave.
Right.
You could potentially see, for example, the ionospheres of exoplanets.
Oh, interesting.
Mm-hmm. Those things snap, crackle, and pop, and make all kinds of noise, but they're really low frequency. And on Earth, you're under our own of the same thing.
Yeah.
And there's plasma between you and space, and plasma reflects radio waves. So it's like looking up at a big mirror that's going pop, pop, pop.
Right.
So going to the moon, you don't have any of that. It's nice, quiet, stable. You have to go to the far side.
Right.
You can only observe it at night when the sun isn't going.
Right.
Crackle pop. But you could potentially see a lot of interesting things about stars and exoplanets and who knows what else. Nobody's ever looked at these wavelengths before. It's just not possible on Earth.
That is amazing. So obviously, in order to enable that, you have to be all in on space exploration.
Right.
So what are your thoughts about what's happening in space exploration right now? Because there seems to be a flurry of activity.
Yeah. It's been a really interesting time. I mean, it's almost impossible to keep up at this point, really, because there's so much action, commercial action. So many different companies doing things. For every sort of splashy, SpaceX landing or whatever, there's a dozen other things that are just as commercially impactful, but sort of less showy.
Really?
Yeah, and there's been a fairly interesting, and I'm not a business guy. I went into academia because of that, so I don't always understand what's going on, and kind of glad of that. But at the same time, anyway, there's been a lot of there was this sort of wave of first we had this sort of maybe about a decade ago we had a really sharp uprise in people building these small CubeSats and people trying to make commercial space happen. And those are kind of orbiting each other. One's obviously a much bigger thing than the other. But there were a lot of companies that were selling regular people, meaning like, universities and other companies, components, small pointing systems, little tiny rockets, radios, I don't know, stuff like that,
right,
for space. And now, a decade later, there's huge inflation in the number of small sats up there. Everything from the Planet Labs, Earth observing CubeSats, which image the Earth once every day, and there's hundreds of them. They're some of the single largest by fraction. That they basically are all CubeSats right now.
That's amazing.
And then things like Starlink and these other things, just floods of stuff in low Earth orbit.
What are your thoughts about Starlink, by the way?
It's great, I guess. I mean,
Does it affect that astronomical sort of observations that we're trying to make in a negative way, or do you feel like the long-term positive definitely outweighs the short-term negative?
It's a commons issue.
What does that mean?
So, when I say commons, I'm referring to in the sort of Old English sense.
Okay.
Of, common. The
Commonwealth,
be land,
right?
Held in the common good, used by the people, sort of communally,
right?
This is, the space between us and the stars is similarly common, commonly held by all of us. The use of that space then needs to be, we need to cooperate. And we have been, like, there's all kinds of treaties and other things in place, and bad actors tend to get quite a lot of opprobrium. So a few years ago there were anti-satellite tests, and there was a lot of hubbub about that. And recently the China booster landing in whereversville a couple of weeks ago is another example. The one that I'm most familiar with is radio coordination. Not just radio astronomy, but if you want to talk to your satellite, you need an FCC license in this country, and internationally, there's a coordination process to make sure we're all on different frequencies and stuff like that.
Yeah,
and we coordinate and we talk to each other. I don't know how that's going for Starlink. So
is it a voluntary thing? It's like don't they have to be coordinating with others?
I mean, anything international is voluntary, man.
Okay, gotcha. But aren't they coordinating with like NASA for some of this stuff? And
I mean, so they must be coordinating with the FCC. The FCC regulates,
like U.S. communication for sure.
Telecommunications for any U.S.-based company or person or anybody. They also regulate, because they do, and you have to talk to your satellite over radio.
Yeah.
They also effectively regulate, space. They for example, evaluate your satellite.
The FCC regulates space for that reason.
Effectively.
Yeah.
Which is kind of weird. and maybe not what you might have picked
as the organization
as the
to
organization to do that. So they must have coordinated there. There's going to be some tricks. So, for example, I know that SpaceX is sponsoring some research at the National Radio Astronomy Observatory to figure out how to coexist Starlink with radio telescopes, which are incredibly sensitive, and if you transmit in the beam, you could literally fry the receiver.
Oh, wow.
I mean, these receivers can detect the Big Bang, the dawn of time. They're very sensitive
from billions of years ago.
Yeah,
So.
they're very, very sensitive. So if you, it's possible to blow them up. And so you do that. You figure out how to work around it. And the optical astronomers also have a beef, about occlusion and reflection and stuff like that. I'm pretty confident that Leo is not a great place for this. I think
Leo being low Earth
orbit. Yeah, I don't know. I have a suspicion that we're not going to be. You're not going to go outside of 100 years from now and just see a billion speeding lights across the sky. I don't think that is where we're headed, but I could be wrong, and that could be one outcome. And I think people ought to be kind of alert to that.
Interesting. Why do you think that satellite communication is not the future?
No, I think it is. I just don't know that.
That low Earth ones are.
Yeah, and you can.
Well, the higher you go, the higher the latency, and latency is what's sort of because of speed of light, right? So that's what kills the high orbit ones.
Yes and no. So the doubling. So for example, the distance between us and low Earth orbit is much, 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 much less than the distance from here to New York.
Yeah.
For example.
Yeah.
So, as long as you're always, you're talking about relative delays that are smaller than the size of the Earth,
right?
You're probably not worrying about it too much. That's my cosmology, foot or a mile kind of.
Yeah. So you're thinking maybe not hundreds of miles, but thousands of miles would be the right sort of. Okay, so I mean, it still would mean that we're going to have thousands of satellites out there, or maybe.
But they may be farther away, and they're less reflective, and they maybe are in elliptical orbits, so that they spend more hang time above specific locations. So I don't know. There's a lot of stuff up there already.
Yeah,
a lot of stuff. So
this is a problem we need to solve irrespective. Then
when I was an undergrad, I did a lot of observing at the local observatory, and the first thing that I saw when I took a picture with the camera on the telescope was this line going across the image, getting bigger and smaller, and some sort of booster, tumbling slowly through my image.
The other night, my wife and I were walking in our backyard, and we looked up, and there was literally dozens of lights going across the sky, and I realized that it has to be the Starlink satellites, because they had just sent a group of 60 of them the day before. So as they sort of start to move into their orbital positions over the Phoenix sky, you could see basically all 60 of them, but you could see 30 or so at a time that were moving across the sky. It's super bright. It was just one of the most amazing sights I had seen. But
but not unlike the lineup to land at Sky Harbor, right?
Except
a lot of other stuff up there.
a lot of them though. A lot more of them.
Yeah.
So what are your sort of overall thoughts about humans in space and space exploration? Do you think we should be trying to colonize Mars, for example? Is that a direction that is useful in your opinion?
Well, you use an interesting word, colonize.
Right. Versus going there for research purposes.
No. Historically, colonies have been efforts to extract resources from someplace.
Right.
whether it's people or sugar or whatever. They're sort of like outposts that are designed to run a mine or whatever, service ships going someplace. They're assets for some country.
So for the purposes of this discussion, let's define it as like a self-sustaining civilization.
I know what you're getting at. What you're getting at is just, should people live on Mars, and should we live on Mars, like and the moon, and
and trying to do it in a sustainable way,
sure,
meaning so that like if something were to happen to the sort of
the point that I'm getting at is that there's always an economic basis to everything we do,
right?
And it kind of has to be, right? Like people do things because they make sense, not because of a dream,
right?
And when things are motivated in that way, there are upsides and downsides. And I think the thing to consider is, so that's why I think the thing to consider is why, not will we or can we.
Yeah,
why are we doing it?
Yeah, I would definitely ask you why, if you thought we should do it. But I was asking you if we should do it in the first place.
Well, so given that framing,
okay.
You have to consider what are the pluses and minuses, right? And some of the pluses are challenging humans and that sort of thing. The kinds of things we'd learn how to do would be beneficial to us, sort of like any kind of growth experience that you might have as growing up. Learning how to manage your biosphere really, really carefully. Well, we should learn how to do that here on Earth, right? But we're not really pushed in that direction,
right?
Although we're starting to be. So going someplace hard would be good for us. The solutions, though, you might be a little bit taken aback by them. So, for example, Mars. To live sustainably on anywhere, you need what? You need energy, you need water, and trace resources of some sort or other. You need like lithium and stuff like that to make batteries and what have you. Okay, so suppose so how do you get those things? You mine them. Yeah. So we're going to go to Mars, and how do you get water? Well, so here on Earth, water falls from the sky, although some places more than others.
And 2/3 is covered by water.
And 2/3 of it is covered by some sort of yucky water, which has things living in it. So, you can just go scoop it up off the ground here. But there, it's probably not in underground lakes or in sheets of like crystalline ice.
Probably frozen.
It's probably of dirty, watery dirt.
Right.
Somehow. So it's going to look a lot like mining.
Yeah.
Where you have like iron ore and you want to extract, or gold, or where you have it's embedded in a matrix and it requires energy and mechanical extraction to do it.
To pull it out. Yeah.
Mm-hmm. Yeah. So suppose water, for example, you might basically imagine something like, I don't know, a hot iron that you run across the surface, and then you suck out the water, and then you scrape the dry dirt off, and you do that again and again and again and again and again, and until you have something that looks kind of like Morenci, strip mine of some sort.
Yeah, I mean,
so
these are the hard challenges that you were talking about that would teach us a bunch of stuff, right?
That's right. But what would it teach us about ourselves? We're awesome. We're humans. We're expanding. We're spreading, and we're strip mining. This planet that has not seen a human footprint. So,
is that bad?
What do you think?
Well, I mean, like you're definitely implying that it's bad.
No, I think people tend to think about things like, can we do it, and not should we.
Okay, so
I like to raise the question that I think people aren't talking about as much, just because I'm contrary, and
But should we not do it because we would have to do mining? I mean, like, is that?
I don't know. What do you think?
I mean, it seems like mining is essential to survival.
It's just one little thing, right? Like, there's probably boring parts of Mars that nobody would care if you mined it.
Right.
And then scrape the dry stuff back in, maybe.
You're suggesting that because Mars has been like pristine for billions of years without human influence, like us going over there and like messing shit up again, just like we've done on Earth, is probably not the best idea.
Well, I think it just, humans do this. We expand, we consume, we use the commons for our own personal gain. We get an idea of what's good for everyone, and then we do it, despite maybe it not being. I don't know. So, I think there are other ways, though.
Other ways to do what?
If we know this about ourselves, and we're really thinking about it, how might we? But it's still necessary. Like, we still need to go to places. We still need to explore. We still need to become better.
Yeah.
Then, just because that there's the possibility that we might, re-Columbus something that, just because it's a possibility doesn't mean we shouldn't do it. It just means we need to think about it.
Right.
So
I'm not sure where you fall on this spectrum of like, should we be going, or like, should we be trying as a civilization to become a multi-planetary civilization? Like, if you would to,
of course we should.
Okay, we should.
Yeah.
So, and to become a multi-planetary civilization, if we were to sort of choose Mars as the first planet to go to, we would have to do the mining there. Like, you can't not mine.
And that's I don't know. So there is a lot of stuff floating around in this solar system. There's watery objects, for example.
So it maybe potentially utilize like asteroids and things to get the resources that we need.
And maybe that's a better place to live, honestly. Mars is like, it has an atmosphere, and we can fly helicopters in it, but it's not very thick. What's the cosmic ray situation like? Actually, that's probably well known, but I don't know. But it's you're down a well, which means you need to spend energy to get out of it.
Right.
Gravity well. The benefits of being on a planet might not be as good as you think they are. On the other hand, it might be that people just can't, humans are we're looking at a million years of evolution before we can live in space productively. Without gravity.
Right.
Gravity is pretty essential to everything we do. You can, a really great, really terrible way to kill a person is to hang them upside down.
Right.
And leave them there. So we need to be pointed up in a gravitational field. That's what we need. On the other hand, you just go to space, get enough mass and spin it up.
Yeah.
And then you have gravity. And then you're not in a well, and you can go wherever you want.
So actually, Jeff Bezos has the I forget what they're called. His dream of the future, in contrast to multiplanetary, is that we will live in space.
Rings.
And
rings. Just rings.
Rings.
Yeah.
I don't think they were ring shaped, the structures that he had sort of shown off, but I don't know if they necessarily had gravity, but he, let's call them rings. So your view is that, if in order for human survival long term, we should be exploring space, but not necessarily colonizing planets. We could colonize these rings that we make out of asteroids and resources.
Or just inside of them.
Inside of asteroids, potentially.
Yeah. Yeah, there's a lot of material that, the value of matter that's not on a planet is millions, thousands and thousands of times higher than matter that is on a planet, because it costs so much to get it out of a well.
Right.
Even after you account for reusable rockets.
Yeah. Super interesting. So, who do you like in terms of, who's doing a great job of the space exploration aspect of what humanity is doing right now? Is the European Space Agency? Is it NASA? Is it private companies like SpaceX or Blue Origin? Or Like, what are you excited about in that realm?
Oh, geez. I mean, I'm not gonna pick any. I think it changes so quickly, and once you start, the grass is always greener.
Yeah.
So I think they're all doing a good job. I think, Elon definitely has that kind of Steve Jobs kind of making it happen kind of thing going on, which is good. It doesn't last beyond one person.
Right.
So,
but there's a lot that can be done in one person's lifetime, which is good, right?
it can. We're still, as a species, every 400 years between, average of a couple hundred years between Newton's.
Yeah. But like between famous ones, right? Like if you take humanity in 1950. When was the first satellite? 59.
58.
58 when Sputnik went out. Right? Like
that was 57. Anyway.
Like U.S. didn't even have the ability to send satellites into space in 1960. But by 1969, in less than a decade, we went from not being able to send anything to space to like landing humans on the moon.
That's right.
Which is a feat we haven't been able to replicate ever since, which is kind of mind blowing. In the 60 or 50 plus years since. So there is a lot to be said for someone who is hell-bent on doing a lot of stuff in a short period of time, like Elon is, right? Like the amount that he might be able to push things forward could be actually pretty significant, to the point where we might actually be able to colonize Mars during his lifetime.
Yeah.
And if he wasn't hell-bent on doing that, it's quite possible it might not happen for hundreds of years, and by then, who knows, we might lose the technology to be able to do it, and it might never happen.
Yeah, that's true.
So, like, what's your viewpoint? Like, does someone like Elon Musk, I guess, like excite you, or does he present a risk factor that is like?
Oh, he doesn't present a risk. I just think it's we went to the moon because of the Cold War.
Right.
Going to Mars because of a interesting confluence of economic factors which allow a few people to accumulate an insane amount of wealth.
Right.
Neither of those two things are good. Right? You would agree the Cold War is bad.
I agree.
And
I mean, it definitely had some good elements that came out of it, right?
There's always a silver lining, but we probably shouldn't
Cold War
have
is
gone
definitely
down that road.
better than a hot war.
You're right. You're right about that.
I mean, there was a lot of hot wars before the Cold War, which is the reason that like maybe Cold War is not all that bad, right? Like I mean, I don't know. I mean, I'm sort of like throwing stuff out there just to sort of challenge this sort of assumption that anything with the word war is bad. I think the like actual war where people are dying is bad. Cold War is sort of like a competition in a sense of ideas and
if it were just that, I would agree with you.
Yeah, I mean, but the side wars that they were fighting, I guess,
Vietnam was a bad thing.
Couldn't agree more there. But
but
that was a real war. I mean, like you could have a Cold War without those wars, though, technically speaking.
But we could try again and see how it goes. But I think it was competition,
yeah,
right? And whether it's trillionaires competing, or whether it's economic ideas competing, that's the kind of thing that seems to be the most effective driver of things. And what's not effective is sort of business as usual, military industrial complex, for example, had its fingers all over the shuttle, and that just went nowhere. And
right.
It went somewhere.
way too expensive. And
It was too expensive
not
and
sustainable.
and just had too many silly things going on, basically. So are we going to have every 50 years some outlier economic event that leads to a spurt of interesting activity, and then 40 years of the bureaucrats sort of cleaning up the mess and trying to do business as usual, like Apple is right now, right?
Right.
Marking time until the next big inflection point, or can we do something different? And that's kind of the thing that I'm interested in, and I don't have an answer for you.
Yeah.
But
so okay, let me argue the point of like the can we do something different aspect of it is that maybe this is a good system because it encourages the next Steve Jobs to challenge the Apples of the world who are complacent, right? And we have a system in place. Granted, there's plenty of problems with the system, but we have a system in place that encourages that competition and encourages the sort of next Steve Jobses, and it rewards them probably too well, right? Financially, especially, and in terms of like power and such. But there is incentives in place with the ability for those challenges to come about. Whereas if you don't have an alternative to this system that has resulted in so much progress in such short periods of time, then like how could we say that this is bad necessarily? And this is an honest question. I mean, I'm like, there's lots of things I love about capitalism, but there's lots of things that like truly are a concern, right? Like,
yeah,
capitalism.
I think we're close.
Right.
Actually, I think we're close. I think well-managed capitalism is probably the most successful we've ever been in this country. Anyway, we've had times when, in the 50s, if you got to a certain level of income, effectively you were you were taxed, and all the rest went to the government, and I guess you got a trophy or something, a plaque
Right.
to hang on the wall, and that is how we got to the moon, right? That's what paid for all that stuff was really, really high taxes on rich people, and there's still a huge margin there to do your own stuff, right? You just don't get to become your own little country.
Yeah.
And I think, could under the sort of progressive taxes of the 50s, where we have managed capitalism basically at top end, you could still get the kind of innovation that, in fact, you get more of it because you have more people getting free college, or more people with more opportunities, so they aren't loaded down with student debt or whatever, so that they can actually do things. You can get Steve Jobs is the number of opportunities he had. People talk about privileges a lot.
Right.
I think just the past had more privileges than the present, right? And that's messed up. Like, that's not better. That's so I think that there's just slight adjustments. There can be a lot more people coming up with ways to do things without strip mining Mars, and doing things in a cool way.
Okay. Very cool. So let me change subjects on you for a moment, because ASU is doing lots of cool stuff. First of all, what brought you to ASU?
Oh, well, I came as a postdoc, which is a journeyman scientist kind of thing. After you get your PhD, you still don't know what you're doing.
Okay.
So you take these little jobs that last a few years, and I ended up staying here for 6 years doing that.
Okay.
First working for ASU, and then as an NSF fellow, and then after a while, the opportunity came to join the department where I already was as a professor, and with a focus on the cosmology stuff that we talked about at the beginning, but also helping to make the school, grow its space program, basically, do more instrumentation, more of our own missions in space, and particularly in small satellites, because that was kind of the thing I was into and knew about already.
Right. And like, did you end up loving Arizona as well? As a result of, you're just smiling because. What is that smile about? It's a little like, oh, no, I don't know about that.
I like my job very much.
Okay,
so I am here.
You loved. Okay, you fell in love with the work that you were doing as opposed to.
Yeah, I love the job. I love the people. University is great.
Yeah. So talk about some of the stuff that ASU doing that is most exciting to you.
Well, the ASU is huge.
Yeah.
And so there's...
What is it now, like 100,000 students or
it's
something?
something like that. I mean, it depends on how you count. I think there's roughly 60,000 on the Tempe campus, which is where I'm at.
Wow.
And that's students. And there are a lot of things, faculty, research departments, all kinds of things. Whenever somebody says, oh, that's happening, I didn't know about that, I say, well, there's actually probably another one of those somewhere else that you don't know about. But there's it's so big as to be overwhelming. Anything that you have to sort of start ignoring cool things, which is a good problem to have, or just saying no to things is that's the limiting factor, is your time to just sort of do cool things. So some of the things that I'm involved in, that I know about, that are cool. Well, first of all, I must say that the way that the university handled the coronavirus was very impressive. Universities are not always known for management.
Yeah.
Doing things that people appreciate or like, or doing things well, efficiently. Faculty are, we're the sort of scatterbrained intellectuals, losing our papers walking across campus. But the university stood up testing and sequencing and had, fairly sensible plans in place despite nobody knowing what was going on. I was impressed with the degree to which I signed up for it, and very quickly I could sign up for a test and go get it right away when nobody else could get tested, for example. That was just really, really impressive. So I'm in the School of Earth and Space Exploration, which is sort of like a mixture of geology and astronomy. And the reason is because there are a lot of people interested in planetary science, which is rocks in space, basically.
Right.
And also life in space, astrobiology, where everything from the atmospheres of potential planets to, asteroids. We have one of the premier asteroid centers, meteorite centers in the country here. I'm also involved in the Interplanetary Initiative, which is this sort of pan-university effort, so across all of the campuses, and to ask the questions that a lot of the questions that we were asking today about how humans become an interplanetary species, like everything from political questions, political science, to psychology and sociology and art and law, and all the other, more arcane things that, kind of need to be asked. And every time humans expand, they change a little bit.
Right.
So what does that change look like for us? And that's a big interdisciplinary project with all kinds of different things going on, from a new major made just for that, but to little pilot projects, which are meant to grow into new areas of research, to events and things like that. We also have a lab, and that's the thing that I've been focusing on.
Okay.
It's kind of like a maker space for space.
Oh, nice.
Space maker space. It's a place that students or outside partners, anybody really, can come to collaborate with us on building satellites, instruments, basically anything. Like, I'm expecting weird art projects and all kinds of other stuff to come in. So we have basically everything you need to make a satellite. We have electronics stuff. We have people that specialize in mechanical things and orbital dynamics and stuff like that. But we also have test facilities, so you can come and put if you want to build a CubeSat in your garage, you can bring it down to our lab and put it on. We have a vibe table, which is basically like a big speaker that shakes like it would on a rocket, which is
to test it out, to make sure that it doesn't break.
Doesn't fall apart. Yeah, they do usually the first time. And then we have a vacuum chamber, so you can put it in there and suck out all the air. And pretty soon we'll have a cold maker in there, so it'll get down to about 70 Kelvin, which is cold. That's as cold as you can go on a reasonable budget. It's pretty dang cold.
Yeah.
And other stuff like that. It's ASU is very creative in its use of space. It's the lab is in a gymnasium.
Oh.
From the 50s.
Okay.
It's in the middle of campus.
Is that the one next to the MU?
Yep.
So it's been repurposed. I used to play basketball there.
A lot of people are saying that to me. So when you played basketball there, did you use the locker room?
No.
It was probably gross.
I don't remember ever going into the locker room.
The locker room was very gross. So that's where the lab is now.
Okay.
We took the
how funny.
We took it down to the dirt.
Okay.
And out to the studs. And maybe in some cases past the studs, cleaned off 60 years of funk.
So is the gym still there?
The gym is still there for now. In fact, it's a COVID
funny.
Testing facility right now.
Okay. But the locker rooms are the lab.
The locker rooms are now a space lab.
Very cool.
Yeah.
And that's, you run that essentially.
That's right.
That's
we
awesome.
have a whole crew.
I have to come visit you.
You should. It's pretty cool. We're having a growth period right now. We're taking on new projects and sort of partnering with companies and that sort of thing. And basically anybody that if you're running a company and there's a lot of, like I said before, there's a lot of companies that are building new gadgets and gizmos and things for space because it's becoming this commercial enterprise, and there's a lot of little mom and pop.
Is there any kind of like competition for like encouraging this type of work?
Through NASA and a few other things, you can apply for these grants. If you have a little company, you can apply for grants. We don't have any competitions. We are equal opportunity. Come right now. We have.
Would you want to put on your own competition? If you had would like a $10,000 competition be a thing like that would encourage people?
Sure. If that seems like the kind of thing that would motivate people to do cool stuff, yes.
Yeah, I mean, like I'd be willing to support something like that for building some cool space CubeSat that would actually make it to space. Should we put on a competition?
I don't see why not. Yeah, I have to talk to my our high council for budgetary things. But yeah, I don't see why not. That seems like a good idea. I think
be something fun to do.
What we're trying to do right now is really just get the word out and sort of build up our network of people that might be interested in such things. That way, we kind of have we've got a sense which way the wind's going. So, for example, if we're going to have a competition, I would want to say make it be a little bit more specific instead of say bring competition to do cool space stuff. I'd say something like make a lunar rover that can fit inside a shoebox or something like that.
That's what I'm talking about.
Or could last more than a day.
Or a much better version of the Mars.
A better Mars helicopter.
Helicopter.
Sure.
I mean, like.
I don't think you could do better than what they've got right now.
Although the atmosphere is a problem. On the moon, you have no atmosphere, so maybe
helicopters aren't going to fly on the moon. But
maybe a fast RC.
There are actually other competitions that are going on right now. We had a student team in over this last summer who were working on a probe into on the moon. There are these regions that never see sunlight.
Yeah,
permanently shadowed regions, and they might collect water. They're like a cold trap. They're sort of like the element in your fridge that gets covered in ice, right? And so they're building probes to go in there, and those things get down to like a few Kelvin. They're cold.
Now, how would you like power something like that?
Well, that's a good question.
Yeah.
they were
come
talking
back to
about
the sun. Every now
they
and
were
then.
talking about just charging up a battery and just shooting it in there like a bullet and learning whatever they could until it died.
Gotcha.
Other people were like, talking about, I don't know, nuclear power is basically the best, as far as I can tell, the best way to do that. But
Yeah.
boy, that's we're kind of running out of plutonium in this country.
Yeah. you set up all the solar panels on the edge of.
Other people talk about that, just a long extension cord, wireless power, laser. You can power things. So one of my other projects is a drone-based radio calibrator, because we find that it's necessary to put an antenna with a transmitter above our radio telescopes.
Yeah.
And I have been doing this for about a decade, and just watching drones sort of go through the entire cycle of, from a decade ago to now, all kinds of nutty things, including a lot of wireless power.
Yeah.
Drones powered by fiber.
Wow.
Laser power going to a light sense, a light absorber, just like a solar panel.
Well, yeah, that's interesting.
Yeah, all kinds of stuff like that. There's a lot of weird stuff out there.
Huh.
Wireless RF power transmission. Combustibles, just use something, like hydrogen.
Right.
Burn it. Just burn it. Who cares about the where the products are like water.
Yeah.
So maybe you don't want to do that in the place where you're trying to detect water.
You might have a false positive there. But no, I'm serious about the competition thing. But we can talk about the details.
Yeah, let's talk about it. I think that's a great idea.
Yeah, that would be fun.
We've talked about things like that.
Yeah.
There's definitely stuff like that on the table. So I think the question is who,
Yeah.
and what. And I think if we can pick things that are exciting to people, we will get people, and there will be things.
Yeah.
I think that would be fun.
Is there any plans to like put small, what's it called, telescopes, small, like, the equivalent of like the 8-inch, hobbyist telescope into space?
Yep. So another project we've been working on for a few years now is to make basically an astronomical telescope out of a CubeSat.
Okay.
So like a CubeSat is, like I said before, it's like about the size. This one would be about the size of a box of Cheerios, the family size box, the big one. You can fit about an 8-centimeter aperture mirror in there. Now that's not that big, right? Like you could, you could get that at Walmart.
Okay.
But if that's true in the optical, the ultraviolet is basically invisible to us here on the ground. It's absorbed by the atmosphere, except a little bit over New Zealand, where I once have had the worst sunburn in my life. But mostly, it's absorbed by the atmosphere, and so you just can't do that from the ground. There's a lot of interesting stuff in the ultraviolet, including like galaxies ionizing the hydrogen, but lots and lots of other stuff, including like flares from stars. So the nearest planet to us that we know of, that's not
outside our solar system.
Do you know what it is?
It's like 6 light years away, if I'm not mistaken, right?
3 or 4, yeah.
Oh, is it
Proxima
Centauri? Okay.
Yeah, and it's right next door. I mean, they're talking. So there's the Breakthrough Starshot, which wants to shoot a probe at it and have it get there in our lifetimes. It's that close.
What? How would it get there?
Sorry, that's another thing. The CubeSat wants.
Okay.
We want to. There's a lot of planets that are potentially close to us, but they're mostly orbiting basically red dwarf stars.
Right.
Anything about stars, and like the dimmer they are, the more popular, the more common they are. Like the dimmer they are, the smaller they are. So there's more small ones than there are big ones.
Okay.
Like cookie crumbles. They're just really common. They're everywhere, and they probably have planets.
Yeah.
So if you're going to pick a random planet from in our galaxy, it's probably going to be orbiting a red dwarf star.
Red dwarf, but like 4 light years away is not within our lifetimes of getting there.
I'll explain that in a second.
Okay.
But before you even get there, is it worth going? Is it worth going? And it might not be, because these red dwarf stars flare. Like our stars, like as a 10-year cycle, it's starting up again, by the way.
Okay.
Finally. It is a 10-year flare cycle where every 5 years there's a peak. Every 10 years there's a peak. What is it, cycle? It must be every 5 years. Anyway, there's a peak.
Okay.
And at that, during when it's most active, you get a flare, like a big flare that might cause a power outage or something here on Earth. Like a big, they have an impact on us. Way out here, 8 light minutes away from our star. They happen like once a year, once every 2 years, or something like that.
Around red dwarfs.
Us.
For us, it happens once a year.
Dwarfs, they happen every day.
Okay. Wow.
All the time. And where is the habitable zone for a red dwarf star?
Way too close.
It's it's a coal fire. You got to get really close to be habitable, and you're probably going to be tidally locked at that distance too. So you're close to this thing, and it's just popping. It's just popping with UV and charged particles. We don't know why this happens. It's observed to be true.
Right.
But also, that's about, like what I just told you, it happens a lot, is kind of all we know.
Gotcha.
We don't know a lot about how
with
often.
infrared telescopes, we'd be able to tell a lot more. UV telescopes.
Yeah. They like a flare in the optical looks like a loop. It's like a bright little spot. In UV, it's just like it's super bright.
Right.
So, but we don't know a whole lot because there aren't that many UV telescopes in space, and they have to be in space. You can't see it from down here. So, the idea is, why don't we just put a UV telescope inside a CubeSat?
Yeah.
They're really cheap, and you can throw a whole bunch of them up there and monitor all of these stars that have planets around them and see how often they pop, and see, is it like really so bad that it's just gonna dissolve the atmosphere of the planet or something like that. So this Proxima, this planet that's a few light years away, 3 light years away, I think. It's if you were able to go at the speed of light, you could get there in
3 years.
3 years.
Yeah.
If you could go at 20% of the
Okay.
speed of light, 20% is smaller than 100%. Then you could get there in 20 years or 40 years or something like that, right?
Okay.
So it's not totally unfeasible to take a very small probe, make it be 99.999% reflective, like a mirror, like a really, really good mirror.
Okay.
Like the best mirror that has ever existed, better than any mirror that has ever existed. Very reflective, light, like make it weigh a grape.
Okay.
2 grapes maybe. And then shoot it with a terawatt laser. It's going to accelerate at about 1,000 Gs, and in about seconds to minutes would be at 20% speed of light. So basically shooting a grape at a star that's, in that direction.
But it wouldn't have any sort of ability to, like, communicate back with us because there's not enough equipment.
It's a grape. How could it communicate? No, that's not true. People have made little prototype chipsats that are, the size of a postage stamp, and it has a camera and a radio and everything.
But don't you need instrumentation to antennas and things?
On your wrist, you have something that is literally, weighs a few grapes.
But it barely can communicate 20 feet away. How is this?
But you bought that, at a store. I bet if we spent $500 million, we could make one that works a little better than that, right?
I bet you Apple spent a couple $2 billion to make this thing.
They did, but they were going to make a couple billion of them. So they made, and they don't want them to last forever. They don't want it to work very well. They want it to they want you to come back and buy another.
So you think the technology is there to be able to make something that's super lightweight?
It's definitely possible.
That could communicate.
It's worth trying.
Yeah.
Yeah. And so the people are trying. There's a project called Breakthrough Starshot, which is...
I love that.
Which is... so this is one of the breakthrough initiatives. You may have heard of the other one, Breakthrough Listen, which is looking for... which is a SETI project, extraterrestrial intelligence.
Okay.
It's, mainly sponsored by Russian billionaire Yuri Milner. So there's a sort of whole foundation now around these ideas of large capitalization for really, 20, 40 year projects that take human lifetime to do, really.
Yeah.
And so Starshot is one of those. It's going to take 100 years to figure out how to do this, to make a terawatt laser and to make a probe the size of a grape that you can hear from 4 light years away, and all that sort of stuff.
Not if you were as hell-bent as Elon Musk to want to do it, right? Like somebody's going to come around and be like, we need to do this in my lifetime.
That's right. And so that's what these breakthrough guys have started doing. They have said they are putting their money where their mouth is, and people are working on it. People are being paid to work on this, which is great. And there's going to be a lot of interesting stuff to come out of it. Who knows where it's going to go, but they're trying to do weird things that nobody's ever tried to do before because it was silly. So I'm a big fan of silly things.
And the hope is that we could get it there and back and have it sort of survey the.
No, you would. It's going pretty fast, and so it's never coming back.
It's never coming back.
But you
might be able to get the data back.
Yeah, you would hear from it somehow.
Right.
And actually, ASU is part of this. We're handling the communications question for the initiative in a way that has. Mostly just trying to get more other people to work on it. So there's been a process for call for proposals to investigate different ways of doing it, and people are now in the process of starting those projects. And there's a lot. There's going to be a lot of interesting stuff to come out of it, I'm sure.
Wow, that is really cool.
Yeah.
I can only imagine the challenges. Communicating with something that's going at third of the speed of light would be a fun challenge in itself.
Think about it. We have these telescopes that are gonna blow up when Starlink goes through them. I mean, we've gotten some of the way there, and I think there's a lot of other interesting questions that have nothing to do with this sort of thing. Like, for example, how to transmit quantum information that end up being kind of relevant. You need to be able to interrogate a photon, and stuff like that. And so, when you're trying to talk to a grape that's that far away, you're going to be looking at photon. That's Tuesday. I'll write that down, So it's going to be, I think it's going to be stuff like that ends up being the kind of and who knows what kind of interesting stuff's going to come out of it. I mean, development of a lot, these questions have produced things like GPS and MRIs and stuff like that. I mean, this is where all the really interesting stuff comes from.
That's awesome.
Yeah.
Danny, if you weren't doing research on this stuff, what would you be doing?
Oh gosh, I don't know.
Did you almost become a doctor or lawyer or
something? When I was 10 years old, I thought I wanted to go into special effects. I would build little miniatures and blow them up.
Okay.
That I think I am probably the youngest person that could possibly have gone into that career and still made a career out of it. Probably not even. I would probably be, begrudgingly learning animation or something, or retiring early right now. But
that's funny.
I don't know
cool
stuff.
Why it made me think of you'd be working on the Mission Impossible set, and then there'd still be a space connection because that's where Tom Cruise is going, and somehow you'd be ending, your destiny would be space connected in some way.
Yeah, I think if you think big, it's pretty. It doesn't take long to get bigger than the Earth. I don't know there's a lot of people that don't realize that they're more connected to, I don't know, not just to space but to bigger things than they really are.
Yeah.
So I just keep trying to do cool things, and you never know. You ask me, who knows where I'll be a decade from now doing whatever. I have no idea, but I just keep trying to do cool things.
That's awesome. Thanks for sharing the cool things that you're working on with us.
Yeah, it's been fun.
Yeah, likewise. That's awesome. Thank you, Danny. Appreciate it.
Yeah, thanks.
All right, man. All right, you made it to the end of the episode. I would love to get your feedback, so take a moment to leave a genuine review in your favorite podcast app. That also helps us reach more people. Speaking of reach, if you like a particular episode, be sure to share it with someone who you think would enjoy it. See you next time.
I don't have hobbies. I am a generalist. Like on my desk right now, I have Piketty, Viktor Frankl, and Harry Anderson's book on how to cheat people.
Probably not the best book to be like on your desk. Is like somebody comes in.
It's right there. How to cheat people. Card trick, anyone? I bet you $10 I can make this toothpick disappear.